Yeah, I mean, if it's okay with Professor Pukhlikov.
Yes, it is okay.
Okay.
So, have you started recording?
I don't think so. We should get a notification. I'm just here to see if it works, and then I have to go because I have another meeting I'm late for. So unfortunately, I cannot stay.
Can I just check on the proof 321? It's another one of these proofs where you've done the work, but you didn't tell us all the details, I think.
Rainer, they cannot start recording.
This is this claim. I think in
It's
all
recording now. It's recording.
It is recording.
If you're wishing to talk.
Yes, it's recording. It's recording.
So can I speak?
Yeah, go ahead.
Okay, so rationally connected rational double covers of primitive Fano varieties. So the talk is based on my recent paper, which is on the archive. So rational double covers means that we are considering rational maps of degree 2, and rationally connected means that the source variety, the covering variety, is rationally connected. So I'm working over the field of complex numbers, and I would like to start with the famous Uni Rationality Problem. For a given rationally connected variety x of dimension m, to determine whether there is a rational dominant map from the projective space to x. This problem is very old, and this problem is very open in the sense that there are no known examples of non-unirational rationally connected varieties. Of course, it makes sense only to consider the unirationality problem for rationally connected varieties for the obvious reason. I can say that there are plenty of non-unirationality results, but they are only they all are obtained in the following way. Some differential forms are constructed on the variety, and then of course the variety becomes non-unirational, but on the other hand it means that the variety is not rationally connected. And as for rationally connected varieties, we do not know a lot. However, first of all, I would like to say that Gino Fano, in his talk at the International Congress of Mathematicians in Bologna in 1928, as I put it, insisted that a typical conic bundle over a rational surface is non-unirational. I'm using the word insisted because what I mean is that he conjectured and gave some arguments in his very own style. I have not read his paper, but this is what I was told by Alberto Conte. So he gave some arguments. The arguments do not constitute any proof and cannot be used as a proof, even I think as a starting point, but nevertheless, we all know the power of Fano's intuition. On the other hand, there are plenty of explicit constructions of unirationality. For instance, there is a classical fact that if we consider hypersurfaces of some fixed degree in the projective space and take the dimension of the projective space to be high enough, then the hypersurface becomes unirational. So I give here two references. One is a paper of Alberto Conte and Jacob Moore, developing the classical Italian tradition. And the other is a very well-known paper of Harris, Mazur, and Pandharipanda, who studied the classical proof and made it considerably stronger, in particular, if the classical result was about non-singular hypersurfaces of a fixed degree. They actually proved that it is sufficient to assume that the singular locus has sufficiently high codimensions. So they made the classical arguments much stronger and better working. But these results are explicit and positive. As far as I understand, a similar result, similar fact is true also for complete intersections, in the sense that if we fix the type and make the dimension high enough, so the type of a complete intersection, like, I don't know, 2, 2, 3, 5, and dimension high enough, then the same type of argument, finding a linear subspace, and then using induction works for complete intersections as well. But let us look at the other pole. So these are Fano varieties of very high index. So let us consider non-singular hypersurfaces of index 1. So hypersurfaces of, let us say, degree m+1 in the projective space of dimension m+1. The expected answer to the Uni Rationality problem in this case is no, at least for a Zariski general variety. And the problem is, and so since it is no, and we do not know any example of a rationally connected non-unirational variety, we do not even have a working approach for doing this problem. However, about 25 years ago, Janusz Koller, in his talk at the European Congress of Mathematics, conjectured that on a non-singular hypersurface of index 1, there are no rational surfaces through a point of general position. And of course, if this is shown, this will immediately imply non-unirationality. So we can restate this conjecture in the following way. If we consider the space of irreducible rational curves of a given degree on the hypersurface V through a point of general position, then this space does not contain a rational curve. This would immediately imply Koller's conjecture. However, this conjecture is still an open conjecture, an open problem. However, it motivated a deep study of spaces of rational curves on Fano varieties, various families of Fano varieties. For instance, well, starting with the well-known paper of Roy Beheshti and Jason Starr, but there are quite a few other papers. These spaces were studied and their properties, and quite a few results were shown. However, not what was actually conjectured at the beginning. And so the Uni Rationality problem is still absolutely open. So now let us get a bit closer to the topic of my talk. So let us consider again non-singular hypersurfaces of index 1 in the projective space and of dimension at least 5. And the main result, which I'm going to discuss in this talk, is that there are no rational maps of degree 2 onto such hypersurfaces with the target variety, with the source variety rationally connected. In fact, the same, more or less the same arguments prove a more general claim that there are no non-trivial rational Galois covers. So that is rational maps such that the corresponding extension is a Galois extension of degree at least 2 from a rationally connected variety X with an abelian Galois group. But the result about rational maps of degree 2 seems to me most important because it covers all rational maps of degree 2, of course, because they are all Galois rational covers. And this result motivates the following conjecture on absolute rigidity. So the conjecture is that for a general non-singular hypersurface of index 1 and of dimension at least 5, so the same family as in the main theorem, every rational dominant map from a rationally connected variety of the same dimension is a birational map. So compared to the Uni Rationality Problem, this conjecture, and actually, the main theorem, of course, considers a very, very small bit, only rational maps of degree 2. On the other hand, it shows that it makes sense to consider this problem in a much more general context of maps from any rationally connected variety, or maybe some large class of rationally connected varieties, not necessarily from the projective space. So, and this is the conjecture. Absolute rigidity, it is well known that a general non-singular hypersurface of index 1 is birationally super rigid. So basically, it means that there are very, very few rational maps from a rationally connected variety to V, only birational, and the outcome of the log minimal model program for such variety X will be just V. Now let me discuss what I mean by the property Zariski general. So basically, I need only one property of the hypersurface V. Let us give the following definition. We say that a projective factorial variety with at most terminal singularities and Picard group generated by the canonical class, which is anti-ample, so a primitive Fano variety, is divisorially canonical if every, let us say, effective Q divisor, which is equivalent to minus canonical class, has canonical singularities. So we normalize in this, what you see on the screen, we normalize D, we consider an effective divisor, we normalize it by dividing by N so that it is 1 over N, D is equivalent to anti-canonical class. And then for every exceptional divisor over V, the inequality which is opposite to the Noether-Fano inequality must be satisfied. In other words, it means that the global canonical threshold of the hypersurface V is at least 1. So let me just make one remark. If we want to prove that a variety is birationally super rigid, then we need to prove the same property, however, for a general divisor D in a mobile linear system. And this is much weaker than the property of being divisorially canonical. In particular, every divisorially canonical variety is automatically birationally super rigid. Okay, and it was shown in my paper published in Izvestia in 2005 that a Zariski general non-singular hypersurface of index 1 is divisorially canonical for M at least 5. And basically, what I need in the main theorem is the hypersurface V should be divisorially canonical. This is the only property that is really used. And since we know that Zariski general non-singular hypersurface is divisorially canonical, that's how we get the claim. Okay, and so in fact, we could restate the main theorem for any divisorially canonical primitive Fano variety, but then we need a couple of additional properties which are very easy to check for hypersurfaces. And similarly, we can also state the general conjecture on absolute rigidity for a divisorially canonical variety as follows. Every rational dominant map from a rationally connected variety of the same dimension is a birational map. So in my talk, I'm going to explain in some detail how the main theorem is proven. So I will consider only the case of double covers because the case of a cyclic cover is very similar, and the case of a Galois rational cover can be reduced in one line argument to the case of a cyclic cover of a prime order. So the case when the prime is equal to 2 is the most important one. So let us assume they converse, that there is a rational map from a rationally connected variety X to a divisorially canonical hypersurface of index 1, non-singular hypersurface of index 1 in the projective space.
Sasha, a question.
Yeah.
When we use saying about Zariski general, what does it mean? First, you fix degree of the map, right?
No. Zariski general hypersurface. Zariski general means only for hypersurface. So in the parameter space of hypersurfaces of the fixed degree, there is a non-empty Zariski open space, open set, and we can take any hypersurface. And for that hypersurface, there are no rationally connected rational double covers. And actually, yes, cyclic cover.
This is for double cover, but for degree D.
For degree D, we only need to consider a cyclic cyclic cover of a prime order, because this can be easily reduced to the case of a cyclic cover. We just yeah.
But my question is, what do you fix first?
A hypersurface.
Degree or
a hypersurface.
Hypersurface. First, you fix degree and you say that.
No, I do not fix a degree. I fix a hypersurface, and then for any degree.
For any degree, I see.
And for any rationally connected Galois cover with an abelian Galois group, there are no rationally connected maps from a rational map from a rationally connected variety.
Okay, thanks.
Okay, so but in the talk I will consider only double covers because it is more convenient, and basically the proof is the same, argument is the same. So we can desingularize, desingularize X and desingularize the rational map. So we can consider the case of a morphism which is of generic degree 2. So let us start with considering the following toy example, which is of course something very obvious. So why it is not possible to just construct a Fano variety as a double cover over V branched over a non-singular hypersurface in in the in V, so that X is rationally connected or a Fano variety. And of course, the reason is that the anti-canonical class of V is too small because V has index 1. So we just use the Hurwitz formula, and we see that if the branch divisor is of degree is cut out by a hypersurface of degree at least 2, then the canonical class upstairs will be effective. So it cannot be rationally connected. So if we want to construct a double cover, we need to consider the case when the branch divisor is either hyperplane section or it is unramified at all. And both cases are clearly impossible. And actually, this toy example is quite meaningful because for hypersurfaces of high index, we can construct plenty of double covers or even cyclic covers, which are Fano varieties and so rationally connected. So this is a toy example, and I will keep it in mind. But consider, of course, the general case. So for the general case, so let me remind you that we have a morphism from some rationally connected variety X to V, and this morphism is generically of degree 2. So on X, first of all, we take a free family of non-singular rational curves. So what I call a free family of rational curves, I require only one property to begin with. It is that if we consider any subvariety of codimension at least 2, then the curves in this family which meet that subvariety form a proper closed subfamily of our family. So a general curve does not meet any fixed subvariety of codimension at least 2. So of course the open set in the family depends on the subvariety, but nevertheless. So our reference is the very well-known Kohler's book on rational curves. And let me just explain in a couple of words, why can we be sure that such a family exists? So if we have a morphism from P1 to a non-singular rational curve in X, which is an isomorphism onto the image, for a rationally connected variety, we can always find a morphism such that the pullback of the tangent bundle of X is ample. So it is a direct sum of ample line bundles. And so these are the arguments from Kohler's book. The deformations of the morphism are unabstracted, and the curve can be deformed at any point in an arbitrary direction, and in fact, even at any 2 distinct points in independent directions. So that's how we can deform a curve from any subvariety of codimension 2. And so this is a picture. So if by chance C is meeting Y, then of course we can find a vector field, and the deformations are unabstracted, so we can deform the curve away from the subvariety. But I would also need a couple of other properties from the curves of our family. So the first one is that for every prime divisor in X, such that at the general point of that divisor, we do not have an isomorphism of the tangent spaces, a general curve meets the divisor transversally at points of general position. And the second property is that for a general curve in our family, the morphism from X to V is birational on the curve. So again, this is a picture. Since we can deform at two distinct points in independent directions, if by chance the morphism sigma restricted to C is not birational, so it is a double cover, we can deform it slightly and get a birational map. Okay, and now what we do? We map the family from X to V using our morphism sigma. And now the family of curves that we get on V is not a free family of curves. And the reason is very clear. So if our original family of curves on X, we should expect it to cut every subvariety of codimension 1, every divisor on X, then when we apply sigma, if the divisor is contracted to a subvariety of higher codimension, then of course all rational curves in our family will meet that subvariety. So, the family is not free. And the first technical fact is that we can apply a sequence of blow-ups to V such that the strict transform of our family on V plus will be a free family of curves. That is, for every subvariety of codimension 2 or higher, a general curve will be not meeting that subvariety. And it is quite easy. I mean, it only requires elementary algebraic geometry to prove that technical fact. So if there is a point through which all curves in our family pass, then we blow such point. So we blow all such points until there are no points lying on all curves in our family. And then we look at curves, and then we blow up curves, and so on. Okay, so we obtain some blow up of our hypersurface with which we started. And on that variety, we have a free family of curves. And note that when we take any curve in that family, when we take its inverse image on X, then it will be a union of two rational curves by construction. So the technical fact too is that now we can also modify X. So over an open subset, Zariski open subset in V plus, we can construct a double cover in the usual sense, branched over a non-singular divisor, which is birational to X. So it is essential that the open subset U is obtained from V plus by throwing away some closed subsets of codimension at least 2. So let us look at this diagram. We start with a morphism from X to V of generic degree 2. And phi X is a birational map. U and Ux are quasi-projective varieties, both non-singular quasi-projective varieties. Sigma U is a double cover in the usual sense, branched over a possibly reducible, but nevertheless non-singular hypersurface in U. And codimension of the complement to U in V plus is at least 2. So note that when we are constructing U, we can remove any subset of codimension 2 or higher. That's why the branch divisor can be non-singular and reducible at the same time. So how do we prove that? The field extension is quadratic. So it is generated by some element which satisfies a quadratic equation. So basically, the larger field is obtained by adding some square root of a rational function. And using this fact of elementary algebra, it is possible to realize the variety X as a hypersurface in V plus times P1. And then we can modify, this is also quite elementary, modify this P1 bundle over V plus and construct a locally trivial P1 bundle over an open set U, which is obtained by removing some closed subsets of codimension 2 or higher. And X is realized by a non-singular hypersurface in that P1 bundle given by a quadratic equation. Locally, it is a quadratic equation. And it will be branched over a non-singular hypersurface in U. So what is important here is that when we construct the open set U, we can remove some subsets of codimension 2 or higher, but not a divisor. And for that reason, this operation leaves our family of rational curves unaffected. So the open set U still contains the projective, the general curve of our family, so still contains projective rational curves, because the rational curves in the family, the general curves, do not meet the subsets which we throw away. And now we can complete the proof of the main theorem. So, as I said, a general curve in our family does not meet the complement, and so is contained in U. And again, as we know, the inverse image of that curve with respect to our double cover is a union of two distinct projective rational curves on the quasi-projective variety Ux. So the curves C1 and C2 move in families of rational curves, sweeping out the whole variety. So we have they intersect the canonical class negatively. So Ku means the canonical class upstairs, not downstairs. So it is the canonical class of the variety Ux. Because downstairs we have just the canonical class of the variety V plus, so we do not need that symbol. Now we use the Hurwitz formula like we did in the toy example. W is a non-singular hypersurface, non-singular branch hypersurface of the double cover. So we write down the canonical class of V plus. So it is the pullback of the minus hyperplane section plus the exceptional divisors with discrepancies. And then we separate the components of the branch divisor which are divisorial on our hypersurface and those which are exceptional. So we have this presentation for the branch divisor. And of course, the divisorial part is just the proper strict transform of some divisor, some effective divisor on our hypersurface V, the strict transform on V plus. and then restricted onto U, of course. And the exceptional part is just a sum of a few exceptional divisors, if there are such exceptional divisors which get into the branch divisor. So we get the inequality that which I have already mentioned. And now we will use the property that the canonical class of the hypersurface V, or rather anti-canonical, is not large enough, as in the toy example. So first of all, let us assume that n, so this is the degree of the hypersurface which cuts out the hypersurface divisorial part of the branch divisor. So let us assume that it is higher or equal than 2. Then using this simple manipulation, so adding some negative number to both sides of the previous inequality, we get that C intersects the linear combination of exceptional divisors negatively, which means that at least one of the coefficients must be negative, one of the coefficients in brackets. And this is nothing else but the Noether-Fano inequality for the divisorial part of the branch divisor. So the pair with the divisor 1 over n and the divisorial part of the branch divisor turns out to be not canonical, which contradicts to the property of the variety V. So at this point, let me just remind you the toy example. So we excluded here the case of n higher or equal than 2 for the simple reason that if n is higher or equal than 2, then the canonical divisor of the double cover becomes too large, so it actually becomes effective. So if we consider an arbitrary rational map, then of course we cannot argue in such a simple way. But what we can say, and that's basically how our arguments work, is that if n is higher or equal than 2, then if we want the canonical class upstairs not to be effective, so to be negative on some family of rational curves, this can only happen because the branch divisor is very singular. So it is achieved via singularities. And this is impossible because our variety is divisorially canonical. So we have only two cases remaining. So n is equal to 1 or n is equal to 0. And the cases are easy to exclude. For instance, if our hypersurface has odd degree, so this is the simplest case, then we just take any non-singular curve of any genus meeting that particular hyperplane section transversally outside this prescribed set of codimension at least 2. And then, of course, we have a double cover of non-singular curves branched over an odd number of points, which is impossible. And if the degree of the hypersurface is even, then we can slightly modify this argument and get the same result. And of course, if n is equal to 0, of course, in principle, here we can use topological arguments, but without any topology, we can just find a non-singular rational curve on V which does not meet the same closed set. And then we get a non-ramified double cover of a non-singular rational curve, which is also impossible. So that's how we prove the main theorem. So the proof is now complete. Now let me just mention that basically divisorial canonicity, that property, has been shown for general members of many families of Fano varieties, which are known to be birationally super-rigid. So if we know that something is super-rigid, then, and this is of course not a theorem, just an empirical fact, then a slightly smaller open set in the set of these varieties and the family of these varieties will be divisorially canonical, including singular varieties as well. And so let me just mention some applications, some other applications of the property of being divisorially canonical. So one application is as follows. It is actually why I was interested in that property, why I introduced it. If we consider divisorially canonical primitive Fano varieties, then when we take their finite direct products, then it turns out that every structure of a rationally connected fiber space, that is a fiber space with a general fiber and base rationally connected, is just a projection onto some factor. So we can take a product of some varieties in their direct product and project onto it. And this is everything that we can possibly have if we want to, if we consider rationally connected structures on the variety. And the other application is as follows. Let us consider Fano fiber spaces over a non-singular rationally connected base. What about, so this is sort of a generalization of the well-known Sarkisov theorem for conic bundles, which holds in any dimension. So if we want to study birational geometry of Fano fiber spaces, so fiber spaces, the fibers of which are Fano varieties and the base is rationally connected, this is actually a very difficult object to study, to investigate. But if we consider fiber spaces such that every fiber is divisorially canonical with maybe mildly singular, and satisfies a few additional conditions of general position and some additional global numerical condition, which is similar to the Sarkisov condition for conic bundles, or the K-square condition for fibrations over P1, then it is my result of 2015 published in Izvestia. We can claim that every birational map onto the total space of a rationally connected fiber space factors through the projection pi. So I mentioned some other numerical condition which is similar to the Sarkisov condition. So basically, I do not want to state it precisely in my talk because it actually goes out of the topic of my talk. But I will give an example showing that that numerical condition is actually not really restrictive. So let us consider Fano fiber spaces of the following nature. Let us consider a direct product of two projective spaces, P M+1 and P M small, M-dimensional projective space. And let us consider a hypersurface of by degree m+1 L. So it is obvious that when we project onto the second factor of onto the projective space of dimension m small, then we have a fibration into Fano hypersurfaces of index 1. So this is a Fano-Mori fiber space. When we, of course, so it is assumed to be Zariski general, so we can assume that the singularities are nice. So there is an upper bound for the dimension of the second projective space. It is less or equal than some expression which is quadratic, 1/2 of m squared plus something smaller. So this is because I want every fiber to be divisorially canonical. And if we exceed that dimension of the base, then we cannot hope that every fiber will satisfy the property of divisorial canonicity. So that's the condition of general position. And now we have a numerical condition for the second integer in the by degree. So L is higher or equal than the expression on the right-hand side of that inequality. So then all the assumptions of the previous theorem are satisfied. And if we look at this condition, then m+1 over m for a high enough dimension m is approximately 1. So it is basically something like L is higher or equal than m+1. And in fact, if L is less or equal than m small, then of course the projection onto the first projective space also gives us a structure of a Fano-Mori fiber space. So because we have a fibration into Fano hypersurfaces. So this is, there is a narrow gray area between the cases which obviously where the claim of the theorem is not, it doesn't hold, and the condition of the theorem. But apart from that small narrow gray area, the all cases are actually covered. Okay, so, but this is just about the importance of the condition of divisorial canonicity. Okay, and that's basically all I wanted to say.
Thank you, Sasha. Let us think. Thanks, the speaker. Question, comments, please.
So you need to unmute John Christian.
He can.
He can, because he raised his hand, I think. Oh, okay, I see, yeah.
Oh, I have a question. In your main theorem, how important your hypothesis about the dimension is? You assume that dimension is at least 5, right?
Yeah, because you know, for hypersurfaces, I can only prove divisorial canonicity for dimension at least 5.
I see.
This is the only reason.
But what's your expectation? Because you know that there is famous conjecture about quartic, 3-dimensional quartic.
Well, I think that the general quartic,
yes.
Zariski general quartic, I think it is also divisorially canonical, but it is very hard to prove it.
I see. So, and as I understand, divisorial canonicity a variety, Fano variety, implies this some kind of non-Galois irrationality of general variety, right? Something like that.
What?
Suppose your variety is not is divisorially canonical. Then some kind of you are saying that then typically this implies non-Uni rationality in your
No, not Uni rationality. It
in
implies
in your sense, Galois, abelian.
Yeah.
Yes, absence. Am I correct?
Yeah.
Something like this. Is it precise statement or?
Yeah.
I see. So you can say that all other some other, for example, cyclic covers of projective space of index 1 are also satisfy the condition, right?
Yes, but there are also, there are two cases when in the proof when n is equal to 1 or 0. So basically, they are very simple and very simple to exclude at the very end of the proof. So this is the only reason why I did not consider any other families. So if you can do them as well, then the only thing that is necessary to require is divisorial canonicity, nothing else.
For example, complete intersection as well, right? I see. More questions?
I have small question, basically opposite to what Yuri asked. So, for example, if you take unirational varieties, so do we know many construction of unirational varieties which are Galois?
I don't know.
Okay.
So actually, this is absolutely terra incognita.
Yeah, but Vanya, for example, cubic.
Cubic is unirational, yes.
Of degree 2.
Yeah, cubic of degree 2. Yeah. And for cubic, this condition
but three-dimensional quartic is the construction is not Galois. It's something like degree 6, something like this. This is not a cyclic cover.
But I don't know. It's given implicit, so I never checked an equation. Is it obvious it's not Galois? At least the construction which in your book.
I don't think so. Yes, of course.
Because it's geometric, so but probably it's not Galois. But...
Yes, it's very general, so it's not.
It's not general.
Yeah,
no, you said construction is general.
It's not general, but the cover is not very. I think that it's very far from being cyclic. The cover itself, not the variety. I see.
There was also a question in the chat about is it possible to get slides?
Yeah, why not?
Yeah. So.
But yeah, okay. But basically, the slides were taken from my paper on the archive, and the paper contains more than the slides. But it's not a problem. Should I email the file to you?
Yeah. John said he will check the paper, so it's okay. Maybe.
Okay, and one more question. Suppose we are. Can your method work for Galois cover, not for just abelian?
I think so, but basically, if we have a Galois cover with an arbitrary Galois group, then what suggests that it should work is that the canonical class is invariant under the action of the Galois group. So it should be a pullback of some divisor on the target. So basically, only this is the thing which matters. But on the other hand, it requires some work because an arbitrary group, and we take some Q divisor, which we will get if we consider the action of the Galois group. It will be a Q divisor. So there are some numbers. So it takes some work. Yes, I think so. That it doesn't matter whether the group is abelian or not.
I see. I agree.
Because so that's basically the main point. If we consider an arbitrary rational map onto our hypersurface V, for instance, or any other variety, then the branch divisor, if we resolve or do something like that, then it will be not pulled back from the target. So it is some divisor. We know nothing about the Picard group, for instance, how many divisors are on the covering variety. We know nothing about that. However, if we have a Galois, then we only need to know what the canonical class. And then the canonical class can be expressed in terms of the canonical class downstairs and the Picard group downstairs. And that's the only thing that matters.
I agree. Yes. But it's a good problem. Very good problem. Okay. More questions? If no, let's thank the speaker again. Thank you.
Thank you. Александр Леонидович, извините, что я задержался.
Я все понимаю. Кстати, как мои картинки, они, кстати сказать, выглядели нормально?
Да, вроде хорошо. Вроде хорошо.
Мой был первый опыт работы с этим планшетом.
Я уже привык.
То есть вы преподаете с ним, да?
Да. Ну, я тьюториалы. Да и лекции тоже. У нас лекции записываются, рекордят.
Записываются, да.
Какие-то я тоже с ним. Ну, какие-то я слайды готовлю, а какие-то я делаю типа example класс. Тогда я использую планшет.
И прямо пишете вживую, да, так сказать?
Да. Ну, так иногда удобнее. Потом, когда семинары, там просто они удобно со студентами. Они задают вопросы сразу, можно отвечать. Нет. То есть это удобно.
А это идет через whiteboard или как?
Я использую либо whiteboard, либо еще OneNote, одно из них. Whiteboard тоже нормально, да.
Но не позволяет сохранить.
И с аспирантами мы так общаемся. То есть, а как вот с аспирантами же я же не вижусь. Ну, нельзя встречаться. То есть то же самое, мы встречаемся в Zoom, и так удобно. Ты попишешь, там он попишет. Ну, то есть по-другому как-то нельзя. Но время все равно занимает больше, чем живое общение.
Больше, и вообще тяжелее.
Намного. Что-то семестр ужасный. То есть, ладно. Уходит куча времени, ни на что не хватает. Ладно. Юрий Геннадьевич, спасибо большое тоже это. Все, ладно, тогда, Юрий Геннадьевич, наверное,
да.
Тогда все. До свидания.
Да?
У меня еще встреча сейчас в Zoom, митинг административный через полчаса.
Счастливо.
До свидания, спасибо, до свидания.